Okay. Thank you everybody for joining, and thank you Lydéric for organising such a nice day and such a nice event. It's a real. It's always great to come to Paris, and it's a real privilege to be here at this event. So thank you very much. Today, I'm going to provide an overview of some of our perspective on the field related to nano-confined water at interfaces. I'll give an overview of what I consider to be some of the main issues from a computational perspective in treating nano-confined water solid interfaces. And in the second half, I'll talk about one particular application, and that is the study of the phase behavior of water trapped within a very sub-nanometer confining channel. The work that I talk about in the second half, that's work that's been led really by two outstanding postdocs in the group, Venkat Kapil and Christoph Schran, and it's in collaboration with colleagues and former group members, so Andrea Zen, Ji Chen, and a colleague in Cambridge, Chris Pickard. So, like Misha had in his opening talk, he had a picture of the Earth and the water, and emphasized the importance. As a reminder, water really is our planet's greatest resource. It's ubiquitous. It's essential to life, and many of the contemporary challenges that we have, issues such as energy, health, environment, they are all related to water. Water plays a key role, and in particular, water at interfaces and the desire to get a fundamental understanding of how water flows, like we've seen across membranes, how it dissociates in batteries. These are all interesting fundamental questions that have a direct significance to the planet and to society. But even if you don't care about these sort of global challenges, water is just fascinating. It's an incredibly interesting substance. So in the bulk, it has many, upwards of 20 distinct polymorphic structures for the condensed phase of water, so ice. As a small molecule, it has an exceptionally high boiling point. The solid floats on the liquid. And when it comes to the nanoscale, we've seen talk already about some of the interesting novel phenomena that can occur. This image here is a scanning tunneling microscopy image of water adsorbed on an atomically flat copper surface. It spontaneously forms one-dimensional chains. These chains have a pentagonal building block rather than a hexagonal building block. Experiments out of Manchester suggest that when you confine water between two sheets of graphene, there's a pressure acting upon the water that's confined. It's a lateral tangential pressure. This puts water in a part of the phase diagram that you wouldn't normally expect it to be. It's in a high pressure regime, and you can form a novel structure. So here's a measurement suggesting that you form a square lattice of ice, and there's the measurements from Lydéric's group that predict exceptionally high transport of water through nanotubes. So these are all reasons why we might care about understanding these details of the molecular scale processes of water at interfaces. And we've had a couple of talks this morning from an experimental perspective, discussing the amazing developments that have been made, the amazing experimental advances that have been made over the last decade, enabling us to characterize systems that we wouldn't have dreamt that we could study and understand, just a decade or so ago. And we heard from Benjamin the enormous advances that have been made in classical molecular dynamics approaches, in particular classical molecular dynamics approaches for complex electrolyte solutions. So there have been enormous advances in the field, but still these systems are challenging to probe. And some of the particular challenges that arise come from the fact that water is a closed shell molecule. It interacts weakly with its environment and with itself. And this interaction comes down to a balance of hydrogen bonding interactions and van der Waals dispersion interactions. And this balance of interactions gives you a very rich phase behavior for water. So one way to illustrate this is if you think about water as a hydrogen bonded liquid. So then we have H2O molecules. These are hydrogen bonded to each other. And if you ask, let's take an exceedingly simple arrangement of water molecules. If we take 6 water molecules in a hexamer, so just in the gas phase, not interacting with anything, and if we ask, well, what's the most stable configuration for six water molecules? How do they arrange themselves? Well, this is a topic that's been discussed and measured and debated for upwards of 20 years. And there, I'm just showing you 2 limiting structures on the sort of extremes of possibilities. So one is a cyclic structure where you have a ring with six water molecules, each one donating and accepting a single hydrogen bond. So in this ring, there are 6 hydrogen bonds. Instead, alternatively, you can stack the water molecules on top of each other. So 3 on 3 in this prism configuration. And in this, there are 9 hydrogen bonds. And so if you think that a typical hydrogen bond has an energy of in milli-electron volts of around 200 milli-electron volts, then you might expect a 2 for 600 milli-electron volt difference between these 2 configurations. Whereas in practice, they're essentially degenerate. And that comes about because of the competing effect, so the dispersion force that favors the more compact structure favors the more close-packed compact structure. And it's this balance of dispersion and hydrogen bonding that's really relevant to the phase behavior of water. And so if we extend this then to a situation that we might care about more, so the actual phase diagram of water. So here's a plot of the phase behavior of water as a function of pressure and temperature. So we have the large liquid phase, and at low temperatures and pressures, depending on the particular conditions, we have an enormous variety of ice phases that form. So there's 20 distinct polymorphs of ice, and these. Out of those, most of them are molecular states, and so they're simply just different arrangements of water molecules with different patterns of packing, so different hydrogen bonding and dispersion contributions in each. And the remarkable thing about this phase diagram is for the ice phases, they are confined to within an incredibly narrow energy window. And so here is a plot of experimental lattice energies for some of the 20 polymorphs of ice. These are measurements that were taken from experimental enthalpies, in which out of the enthalpies the 0 point and thermal contributions were extracted to give you experimental estimates of the pure lattice energy in the crystal. And what you can see is that going from ice 1, the stable room temperature polymorph, up to whereas ice 8, the highest pressure polymorph, these are falling within an incredibly narrow energy window of about 5 kcal, 30 to 40 milli-electron volts. So the whole of the ice phase diagram is compressed to within this narrow energy window. If you then ask, well, how does an electronic structure method do at computing the relative energies of these ice polymorphs, then you can pick up density functional theory. So the most widely used electronic structure method for simulations in the condensed phase. And density functional theory is, as you will know, is exact in principle, but in practice we have to make a choice for the electron exchange and correlation component. And there are now an unlimited number of approximations we can make for electron exchange and correlation. And so if you pick up one density functional, you might get one set of points. If you pick up another, you get another set of points. And I'm not labeling which functional is which, because it doesn't particularly matter to this story. The point is that we have density functional theory. It's an incredibly powerful technique. It's been unbelievably useful in understanding water and understanding water at interfaces. But there are real question marks when we come down to these issues of milli-electron volt precision. The approach that we've been using to overcome this, one of the approaches we've been using is a technique known as quantum Monte Carlo. So it's an explicitly correlated electronic structure method, and I'm not going to go into the details. Quantum Monte Carlo has seen a lot of developments over the last couple of decades. In particular, it's now possible, and that's thanks to work from a former colleague of mine, Dario Alfei and Andrea Zen. It's now possible to do demonstrably reliable quantum Monte Carlo simulations for large condensed phase systems. And here's a plot, for example, comparing experimental lattice energies against diffusion Monte Carlo data for some of the ice phases and for other molecular crystals. And what you get out of these are computed numbers that are as accurate, potentially more accurate than the experimental data, because there are often large experimental error bars. So if you take quantum Monte Carlo and you go back to this problem of the relative energies of the ice polymorphs, then we get the following data. So we get measurements from QMC that are right on top of the experimental numbers for any of the ice polymorphs where experimental numbers are available, and in the other systems where there aren't yet any experimental numbers, then we suggest QMC can provide a reference there. Moving to interfaces, the challenges persist. So and they're even more acute. So we've seen an image like this from Benjamin this morning. So water nanodroplet on a substrate. This is a water nanodroplet sitting on a graphene sheet. And Benjamin showed very nicely how the wetting, the contact angle can change depending on whether or not we have an insulating or a metallic material. What this graph illustrates is how incredibly sensitive the contact angle is to small changes in the water surface interaction strength. So this is a plot, and this work was started off by Yasmin, who was a former student in the group. Here's a plot of the binding energy as a function of distance. So this is just a schematic illustration here. So if you take a simple classical interaction potential for a water monomer, single water monomer interacting with a perfect graphene sheet, so with a carbon atom in the graphene sheet, and if you tune the strength of that interaction, and then you go and use that as an interaction, use that strength, the depth of this well, to simulate water droplets, large water droplets with classical water, then you find that a variation of a water surface interaction from something like 70 going down to 100 milli-electron volts changes the wetting properties of the surface from hydrophilic to hydrophobic. And so, again, these are energies that are in the range of accuracy of density functional theory. So if we now ask, well, this quantity, the water surface interaction strength, has a big impact on the water droplet contact angle, what is the correct number? If you go back to density functional theory and you compute binding energy curve for a simple system like this, the water monomer, again you get any number that you want depending upon your choice of functional. For these milli-electron volt, 100, 200 milli-electron volt issues, unless you're exceedingly careful, you can run into large difficulties with density functional theory. So we managed to find the computational resources to tackle this problem with quantum Monte Carlo, diffusion Monte Carlo, and this is the plot that we obtained for the binding curve with DMC. It turns out that progress in DMC reflects progress in the wider field in terms of accurate electronic structure methods for the condensed phase. So there's a lot of exciting development going on with people developing, for example, taking traditional quantum chemistry methods like coupled cluster and developing periodic versions of coupled cluster. Random phase approximation with singles corrections is another technique that's seeing application in the condensed phase. And so with Georg Kresse and Andreas Grüneis, we managed to persuade them to also compute binding curves with these alternative electronic structure methods, and now we have sort of consensus there. But maybe you don't care about the depth of this binding curve. One of the reasons why we're doing this type of work is to shed light on the performance of density functional theory. And I'm not going to go into that today, but these types of binding curves, these types of reference data sets for the condensed phases of ice, for water interacting with carbon sheets, with nanotubes, all different environments, these can be used to provide insight into the performance of density functional theory, and also to provide insight and to train classical interatomic potentials. And that's one of the reasons we're pursuing this line of research. The second aspect is again, I just show energies here, but we can get our electronic structures out of these systems. And in many of these systems, we see very subtle charge transfer effects from the molecule to the graphene, and this depends subtly on the orientation of the molecules. And that's another interesting piece of sort of chemistry that you can get out of this type of work. So I sort of said that there's this interplay of energies and structures. You get this rich variety of structures because we're talking about energies within a very narrow window. And related to that, then this implies that you can have interesting dynamics. So if you have a wide variety of structures that are thermally accessible, then you will have exchange between these two structures. And in trying to understand interfacial water, then there are these subtle connections between the vibrations, the phonon modes of the substrate, and the phonon modes of the liquid that can give you an interesting interplay and fascinating transport dynamics across the surface. One other aspect is simply in pure water. If you take liquid water and go into the supercooled regime, there is an interesting phenomenon that in the glass literature is known as dynamical heterogeneity. So if you look at these two simulation boxes here of liquid water in the supercooled regime and above, you're not expected to notice any difference between these two boxes. You don't easily see any difference, and if you analyze the structure and structural properties, the distinction between liquid water at 230 Kelvin and at 273 Kelvin is incredibly subtle. But if you ask about, well, what are the dynamical properties of the molecules in these systems, and if you ask, well, what is the mobility of the particles, then in the room temperature liquid you find a rather inhomogeneous distribution, a rather homogeneous distribution of particle mobilities. In the supercooled regime, you get these spatially separated domains relatively mobile and relatively immobile water molecules. And this again is just one of the challenges that we should be thinking about in simulating and in trying to do experiments in systems where we're going into parts of the phase diagram that we don't normally go into. The final sort of challenge that I will comment on is that we saw in Misha's talk that there were experimental differences between H2O and D2O. So in terms of how energy was transferring to and from the liquid and the graphene sheet, and it's well known that in water we have protons. There's a light mass. Nuclear quantum effects can be important, and in particular, there's quite a lot of evidence for nuclear quantum effects facilitating the motion of water molecules and water clusters on surfaces, and this image that you're seeing here is an image from Carina Morgenstern's group. It's an STM image in which she has deposited water on a copper surface, and what we have here is three peaks here. These correspond to two different types of objects. So the slightly smaller one, this one and this one, corresponds to a water monomer, a single water monomer on the surface. This larger one is a water dimer, and it shows up as a spherical image because it's rotating, and it's rotating in a mechanism that's facilitated by quantum tunneling. It's an exchange process of this hydrogen bond, where you have the role of donor and acceptor changes, and this exchange mechanism is facilitated by quantum tunneling. And there are many other interesting challenges to simulating these types of systems. Interfacial water. Benjamin talked about the challenges in simulating electric fields. It's a vibrant and challenging area. So I just want to talk now about this one application that I promised to talk about of nano-confined water, and the approach that we have taken to tackle this system should, in some of it will be clear already. What we're doing is we're interested in understanding the structure and dynamics of water confined between a narrow and two sheets of graphene. We've said that we need very high accuracy for the water and the water surface interactions. I've mentioned that the dynamics of water can be challenging, and so to tackle this, we rely on quantum Monte Carlo, and in particular quantum Monte Carlo to generate reference data and interaction potentials. It's also used to validate our choice of density functionals, and then we use this high level data to train machine learned interatomic potentials, which we can then have the computational efficiency to then go out and do use enhanced sampling techniques to sample our system with molecular dynamics for a sufficiently long time that we can work out questions like the melting temperature of our nano-confined water or phase transitions between different states. And so the particular system that I'm going to talk about is one that was motivated by experiments in Manchester, in which water was confined between two sheets of graphene, and the structure was characterized. And the suggestion was that you form a square phase of ice. Now the experimental observation is questionable, so it's been contested, and whether or not square ice forms or not is still under debate. what I think is particularly interesting about the experiment, though, was the suggestion as to why the square ice was forming, and it said that when you confine your water between you have a bottom sheet and a top sheet, the top sheet is draped, is like a blanket in a way over the top sheet, over the bottom sheet, and this creates, because the graphene interactions are attractive, we have the van der Waals attraction between these sheets. This creates a pressure, a lateral pressure on the water that is confined. And so this sort of suggestion that in these strongly confined systems, you can have unexpected tangential pressure is something that we thought was worth investigating. And so what we did is we built a system that looked like this, where we have a sheet of graphene. We have a confining potential that mimics graphene on one side. On the bottom side, we explore then the phase behavior of this monolayer confined water within this confining potential as a function of pressure and temperature. And what we do is we do structure searching. So we use a random structure search protocol to characterize stable configurations, and then we use thermodynamic integration techniques, molecular dynamics, to explore phase diagrams, phase boundaries. So here is a plot of temperature as a function of lateral pressure, and the different phases that are observed are color coded. The gray regions are the error bars on our phase boundaries, and what we find at the lowest temperatures and the lowest pressures, we're saying that there's a hexagonal phase of monolayer confined water. So completely expected structure that mimics, that resembles a single layer of ice one. As you increase the pressure, the density increases, and you go from this hexagonal phase to a pentagonal phase, to a square phase, and then to a distorted square, a rhombic phase. And this behavior, this predicted computationally, this is at low temperatures. This has been seen before. This is known. This is expected behavior, and indeed it's getting on for 7 or 8 years ago. Now we did, just with density functional theory, a random structure search for this system, and we found these phases 7 or 8 years ago. But we weren't able then to work out the phase, the melting transition. So we weren't able to do simulations that were sufficiently long enough to give us accurate predictions about the solid, for example, the solid to liquid transition. And now with the machine learning potential that gives us the density functional theory accuracy, we are able to go about doing that. And what that shows is that the melting behavior, so going from the monolayer hexagonal ice in here to where the liquid will appear, there's a significant melting point suppression. So we have a melting temperature of around 200 Kelvin. As we increase the pressure, we get this increase in the melting temperature, and it's a rather non-intuitive transition from being down around 200 degrees to as you'll see getting up above 400 Kelvin. But this phase diagram, before I move on, what we have here is one region at high pressures where we've got a hatched region, and this is telling us that in these pressures around the 1 GPa pressure, the square and the rhombic phase are degenerate. So we can't distinguish them within our computational accuracy. So they're coming within the error bars. If we then look at the rest of the phase diagram, I think then it starts to get even more interesting. And in particular, we have two phases up in this top right hand region. So the brown phase corresponds to something that's a hexatic-like phase, and I will explain what that is in a moment. But it's a state of matter that's intermediate between a solid and a liquid. And the top right hand region, so starting at about 4 GPa and 400 Kelvin, we have another new state that again is intermediate between a solid and a liquid, and this is a superionic state. And I'll explain in a moment what a superionic state is. But the most important aspect of this superionic state is where it's appearing. So it's showing up here at about 400 Kelvin and 4 GPa. And that turns out to be significantly milder conditions than you get for superionic water in the bulk. So if we look at this phase that I described as the hexatic phase, then looking at this line of constant pressure here is useful. So if we explore the changes in the system as we go from 200 Kelvin up above 500 Kelvin at a constant pressure of 0.5 GPa, then we have this data over here. So first of all, if you look at the internal energy of the system, as we increase the temperature, we get a discontinuous jump. So we have a first order phase transition as we cross our phase boundary from solid to liquid. This is reflected in a jump in the diffusion coefficient, and also the 2D distribution function again shows this clear transition from a solid to a liquid. If we look at the same types of quantities now at 1 GPa, what we find is as we cross the first phase boundary, we have a solid to a distinct state, a hexatic-like state. Again, we have this first order transition. The hexatic-like state going to the liquid, there's a continuous second order transition, and this behavior that we are seeing here is entirely consistent with KTHNY theory of melting of two-dimensional solids. And so what we see is going from low temperature to high temperature. We have our solid, in which we have a lattice of water molecules, in which we have, from the structure factor, we have long-range translational order. As we go into the hexatic phase, we still have local six-fold order, but we have lost our long-range translational order. And then in the liquid state, we have lost both short-range and long-range order. And just to sort of illustrate in a movie what this looks like, if I can find my mouse, I cannot find. Oh, it's there. Oh. Anyway, it played. Right. So this is the hexatic phase, a top view and a side view, and what you can see is that you have, if you stare at one particular region, you have retained six-fold symmetry, and the molecules in this lattice are rotating in the plane and from the side view out of the plane. But if you then look across the unit cell and you ask, can you see long-range translational order? Then the long-range translational order is lost. So you have this specific state where we have short-range order and orientationally disordered water molecules, but the long-range order is lost. The second interesting state is the superionic state that I said is appearing, is starting to form at about 4 GPa and 400 Kelvin. So superionic states of water are known, and they were first predicted computationally before they were observed experimentally. And essentially, the sort of simple way superionic states are described is that the oxygens are blue now, is that they're described as a material in which you have a lattice of oxygens and a gas, a delocalized gas of protons. So the oxygens sit on lattice sites, the protons are delocalized. In the bulk, the superionic state only appears at exceedingly high pressures and temperatures, both in order of magnitude higher than what we're seeing, and this means that they're most relevant to the cores of giant planets. In our solar system, that would be Uranus and Neptune. So they only form under these extreme conditions. What we are seeing here under nano confinement is the formation under much milder conditions. And so again, I think a movie illustrates what we're talking about and what we're seeing. And so what I'm going to show you here is part of our molecular dynamics trajectory for this superionic state. So it's a top view. At the outset, water molecules are shown as H2O. So you're seeing the oxygen and both of the hydrogens. Any molecule that's involved in a proton hopping event, so a transfer from one molecule to the next, is labeled blue. And so you can see here we have picked up the simulation at one snapshot. When I play it, you will see these proton transfer events taking place. And so you can see the oxygen lattice is essentially fixed. We're getting proton transfer. Now we're going to coarse grain this, so just the representation, so you only see the lattice of oxygens. And we're showing now a nanosecond of this trajectory. And what you can see, and we're highlighting just particular protons. And again, you can see this lattice of oxygens and this very rapid diffusion of protons through our lattice. So we can then go about quantifying that. And so you can ask, what is the percentage of OH bonds in our system that break in a particular time window? And so you can ask in a very short 100 picosecond time interval, how many of the OH bonds in our system have broken because of a proton hopping event. In bulk ice, so if you ice 7, the phase that becomes superionic, at these conditions, 4 GPa, you get no bond breaking events. In the nano-confined water, as you go from 2 GPa to 3 GPa to 4 GPa, you find that you start to see the significant onset of proton hopping events, of bond breaking events. And at the 4 GPa pressure, it's about a quarter of the OH bonds that have broken in this very short 100 picosecond time interval. And then there's standard techniques that you can use then to estimate the ionic conductivity, and when you do that, when you make with a green Kubo estimate of ionic conductivity, what you find is that you're getting into the superionic regime at about 500 Kelvin in this system. So I will stop there, but before I end, I'll just make sort of 3 comments on where we are with this. So this is a prediction that water can become superionic when it's nano-confined. So first of all, we are working on trying to tweak and tailor the system to understand what can we do to induce the superionic state at even milder conditions. So can we look at confinement within other materials? Can we look at other confinement geometries? The second thing is why does it become superionic at milder conditions? Why does it become superionic more readily in under nano confinement, and that's a rather disappointingly simple explanation. It just comes down to the geometry. So when we have our broken hydrogen bonds, so our dangling hydrogen bonds, this enables the water molecules to come closer together. So for a given increment of applied pressure, water molecules under nano confinement are closer to each other. And the third point I want to make about these systems is it doesn't just need to be water that we confine within these geometries. So there is the possibility of using the pressure that arises from confinement in van der Waals materials to trap other liquids, for example, in particular other hydrogen-rich liquids. And there's a lot of interest in high pressure physics about creating, about accessing high TC with hydrogen-rich materials. And this type of system might be a way to explore that. So with that, I will stop and let you read the conclusions, and thank you all for your attention.